Now, I said we still got 25 minutes left. I want to fill in some geomorphology, and I do want to do some calculations. Many of you asked me how to calculate magnetic declination, and I will spend the last 10 minutes or so on that. But the next one I want to get to is when we're going to have a look at, and we're quickly going to have a look at that, is the following: drainage basins. Okay. When we get to this section, grade 12s, you need to know your concepts. Okay. If you don't know your concepts, you won't be able to answer the questions, because they're going to ask you not to explain the concepts. They're going to give you a diagram, and if you don't know the concept, what it means, you won't be able. They're going to ask you, for instance, what's an interfluve? Why the watershed? What's the name of the watershed that separates drainage basin from A to B? If you don't know what's a watershed, you don't know what to look at. Okay. So what we have over here, first of all, it's a drainage basin. Now define a drainage basin. Okay. It's a river and tributaries and network of streams that drain an area. Now let's just start with the basics. So there's our drainage basin. All rivers, there's J, starts from its source. And eventually where it flows into the ocean is known as the mouth. Okay. Very importantly, other rivers joining the main river, as such, this river over here, is known as tributaries. Okay. Where two rivers meet, for instance over there, is known as confluence. Okay. The high-lying area separating this area over here, separating one tributary from another, is known as a interfluve. What separates one drainage basin from another is known, I just want to use a different color pen, as a watershed. Okay. So that's the basics. You need to know a river originates from its source, ends where the mouth is. The other rivers joining the main river, that's the main river, it's tributaries. The high-lying area between two tributaries are known as the interfluve. When two rivers meet is known as confluence. The high-lying area separates one drainage basin from another is known as a watershed. Okay, that's the basics. Okay, plain basics. You need to be able to know these concepts. Okay. But now when we're going to look at this type of river, we get different types of rivers. And I'm going to move into my next diagram. Okay. There's the source where the river originates. There's the mouth where it ends. There's the tributaries joining the main river. There's the main stream. What do we call this high-lying area between the tributaries? An interfluve. What do we call where rivers meet? Confluence. Okay. Now what we have here is a longitudinal profile, but I'll get to that in a second. But I want to get now to our different rivers. Now, we have permanent rivers. We have episodic, periodic, and exotic. Okay. Now, I'm not going to write it down. You need to listen to me because I want to use more time to explain more stuff. Okay, more content. Periodic, same river that you've been introduced in grade 10. It's the solid blue line. It's known as a perennial river. Okay. Permanent river flows all year round. Okay. high rainfall areas. Doesn't dry up. That's a permanent river. So you know it from grade 10 as a perennial river. That's a permanent river. Moving to our periodic river, okay, that's a solid blue line on map work. It's a dotted blue line, and you know that as a non-perennial river. Okay, what's a non-perennial river? Only usually flow during rainy season. Okay, so usually dries up when there's dry season. Okay, but flows during rainy season. Then we have our episodic river, only flows especially now in Gauteng, many rivers after a flash flood. Okay, immediately after the flood, the water is dry again. Then we got exotic rivers. Once again, we are fortunate. Two of the best examples, one is in South Africa and one is the longest river in the world, the Nile River. Okay, we're going to take you to another image. There's the Orange River. Okay, the Orange River is a beautiful example of an exotic river. Why? Because if you look at the course of the river, right, goes through the Northern Cape. So it's extremely dry and arid region. So it doesn't actually get its water from this region, but where does it get its water from? From the high-lying areas of Lesotho. Okay, so it gets the majority of the water for the Orange River comes from high rainfall areas. Okay. So we say it's exotic because the majority of the course of the river is through a very arid and dry region. So that's exotic. Okay. Now, that's our different types of rivers. And then we talk also, I just want to go over this, we talk about the density of rivers. Okay. Now this is an example of a high density and this is low density. This is a high density river. We have many tributaries. Okay. And then I'm going to explain stream order as well. In a low density, only a few tributaries. Now, rivers have high density or they are low density. Simple reason why is because of the following factors. First of all, the amount of rainfall. Now, just assume there's the high density. Do you agree with me that there's more rainfall at River A than at River B? So, water flows in two ways. Surface runoff, when it's on top of the water surface. Groundwater runoff, when the water infiltrates. Okay, so by the way, these factors very similar to that contributes to the density of rivers. That determines if a river is going to be on top of the surface or when it's going to promote groundwater. Very similar factors. But I'm going to discuss the density. Okay, high density, more rainfall than B. So that's our first factor. Second factor is the gradient. Or we can say the steepness of the slope. Now, the gradient much steeper at the high density than the low density because what happens? It's a steep gradient, the water won't have time to infiltrate. So it's not going to promote groundwater runoff. So the water is rather going to be on top of the surface because there's no time for it to infiltrate. Okay. We have the low density, we can say it's a gentle gradient. The water allows to infiltrate. Okay. Third factor, the permeability of the rock and soil. Okay, when we look at permeability, does it allow water to infiltrate? Now, if you look at the high density, do you think, we talk about Impermeable rock. Impermeable means it doesn't allow the water to infiltrate. So what's it going to promote? High density. The water is rather going to be on top of the surface. With a low density, right, what happens? We say the rock or the soil is permeable. It allows the water to infiltrate. So think of A as the assembly quote. Think of B as the rugby field. It rains. What's going to happen on the assembly quote? It's covered with concrete. The water won't have time to infiltrate. Okay. So it's going to be a high density. You're going to see more actual water. But if you look at the rugby field, it's covered with grass. That's our next factor. What's going to happen? It allows water to infiltrate, creates permeability. So it's going to be a low density. Okay. So, and last one, can mention vegetation cover. Once again, if you look at the drainage basin A, probably not a lot of vegetation cover, because what does water do? It absorbs. It promotes groundwater runoff. Okay, when there's scarce vegetation, right, it's going to, sorry. When it's high, it means there's not a lot of vegetation. When it's low, lots of vegetation, because it promotes groundwater runoff. Now, when we determine density, when you see a lot of tributaries, you know it's high density. You got low density. And it comes with stream order as well. How higher the stream order, how higher the density. Okay, the higher the stream order, higher density. So, pay attention and make notes, because I'm going to give you the formulas for stream order. The first stream order plus a first stream order makes a second stream order. A first and a second stays a second. A second stream order plus a second stream order makes a third stream order. A second plus a third stays a third. A third plus a third makes a fourth stream order. Okay. I doubt that you will get higher than fourth. So this is the formula. I hope you write it down at home, because this question doesn't only come up in your theory paper, but also in your math book paper, to be able to determine the stream order. Okay. And while we at it, each and every single textbook, it's on page, if you use the focus, it's on page 123. You've got a table that shows you the different drainage patterns, the dendritic, the trellis, the rectangular, right? They give you the pattern, they give you the characteristics of it, right? And the description why it is formed according to. It's in every single textbook. I know the textbook because my learners use the focus. Go and study the table, because you need to differentiate between the different drainage patterns. Not only are they going to ask this question, I just want to show you, this is one of the questions. There's it. There's your dendritic, radial, trellis. Okay, there's it. They're going to ask this in your, I just want to go back to my slide. They're going to ask you that question not only in your theory paper, but also in your math book paper. So go and study the table with your different stream patterns. Vitally important. It's going to be in your exam. Every single thing that I've explained to you today is going to be in your question paper tomorrow. I'm not spotting it. I know it's going to be there. Okay. Now, for instance, you look at this. 1 plus 1, that's your formula. So let's quickly do the high drainage density. There's a first stream order and there's a first stream order. So that makes it a second. Am I correct? There's a first stream order and there's a second stream order. It stays a second. There's a first stream order and a second stream order. It stays a second stream order. There's a first stream order, another first stream order. So where the confluence takes place is the second stream order. There's a first stream order and a second stream order. It stays a second. First stream order and a second stream order, it stays a second. A second and a second becomes a third stream order. A first stream order plus a first stream order makes it a second. A first stream order and a second stream order makes it a second. A third and a second stays a third. There's a first stream order, another first stream order, it stays a second. A second and a first stay a second. A second and a third, so drainage basin A is a third stream order. If you look at B, first and the first make a second. First and the second stays a second. Second and the first stay a second. And once again, I come to the conclusion, how higher the stream order, the higher the density. Okay, now, explain that. Now this is our longitudinal profile of a river. Now remember, there's the source, there's the mouth. Where the mouth is, we refer to it as permanent base level of erosion. Okay, it means the river can't erode any further than this. Okay, as you can see, very importantly, look at this beautiful concave profile. So this is known as a graded profile. It's beautifully concave in shape. And what we can do with a river profile longitude, we can divide it up into three courses. So upper, middle, and lower. The upper course, remember, it's where the source is steepest, right? So we only experience vertical erosion. We got a steep valley. What happens in the middle course? Now, more tributaries starts joining. So this is the upper course right there. There's the middle course and there's the lower course. So what happens? The riverbed valley starts to widen because what did we experience? We experienced lateral erosion as well as vertical erosion. The river becomes wider because more volume of water has joined the river. What has happened at the lower course? There's no erosion, only deposition. Okay, so that's our three different courses. Now, very importantly, I just want to show you this. So I've just shown you the course over there is a beautiful concave, and that's a graded profile. Now, we also experience ungraded is when we experience nick points. Remember, that's permanent base level of erosion. Okay, but when we experience a nick point, such as, okay, you can see the profile is not smooth anymore. We refer to it as an ungraded profile. And where the nick point is situated is known as temporary base level of erosion. Okay, now temporary base level of erosion might happen because of rejuvenation or river capture, or more volume of water has been added to the river. Okay, I've got 5 minutes remaining. Many of you on Facebook asked the question, magnetic declination, okay, in your MAPU paper, and I want to explain it to you. It's very simple and it's an easy 5 marks, okay. So I'm quickly going to explain it to you because we're running out of time over here. I've tried my best. Every single question that I've done with you today, not question, but I've shown you, I promise you is going to be in your paper. It might not be the same diagram, but it's very similar. But let's get into it before I waste more time. So, you got your map, paper 2, right? 1 to 50,000 map. And let's call the map Joburg, Pretoria. Okay. And on the bottom of your map, you have your references, you know, keys and whatnot. Okay. And usually in the middle of your map, you'll get a set of information that presents the magnetic declination. And it will go as follows. It will tell you the magnetic declination. I'm just going to use an example. Okay, pay attention. They will tell you is 20 degrees, 14 minutes west, and the map was drawn in 2005. And below it, they mentioned the annual change. Now, every single year, the map was drawn in 2005. Annual means yearly. So the question is going to state, calculate the present magnetic declination. What is the present? 2020. Yes, we want to forget about it, but yes, that's the bloody present year, 2020. So the annual change is 4 minutes west. Remember, grade 12s, we're working with degrees, minutes, and seconds, but we're only dealing with these two. We're dealing with degrees, minutes. Okay, this is key. There's a formula. When it goes west, we add on the end. When it goes east, we subtract. That's a small formula over there. So now the question states, calculate the present magnetic declination. You got this information. It's situated right there in your map. Okay. Magnetic declination is 20 degrees, 14 minutes west. The annual change is 4 minutes west. The map is drawn in 2005. We need to calculate the present magnetic declination. So, 2005, 2020. So, first thing you do, 2020 subtracting 2005 gives me 15. Now, we need to calculate the present magnetic declination. What do we times it with? Times it with 4. Am I correct? Now, what is that? That's minutes. 4 minutes. 15 times 4, you get out your calculator. 15 times 4 gives me 60. Ah, I love this one. This is interesting. Gives me 60 minutes. Grade 12s, we don't talk about 60 minutes, don't, are we? No. What do we talk about? We talk about 1 hour. 60 minutes equals 1 degree. Are you with me? 1 degree. And where did it move to? It moved west. So what are we going to do? We're going to add. So what do we say? 20 degrees, 14 minutes plus 1 degree. What's our final answer? 20 degrees, 14 minutes west. I see we got time. Let's do another one quickly. Okay, let's do another one quickly. Let's say the magnetic declination is 18 degrees for Harry Smith. 21, sorry, just hang on. Almost made a mistake over here because I'm rushing it. It's 21 degrees. Let's try quickly. Okay. 18 degrees, 55 minutes. The map was drawn in 2015. The annual change is 2 minutes west. Okay, so what do we need? We need to calculate the present magnetic declination. 2020 subtracting 2015, that gives me 5. That's 2 minutes. So it's 5 times 2, that gives me what? Calm down, we're going to finish this. Gives me what? 10 minutes. Because we're moving west, what are we going to do? We're going to add. So it's 18 degrees, 55 minutes, plus 10 minutes. 55 minutes plus 10 minutes gives me what? 65 minutes. Am I correct? We don't talk about 65 minutes. That 65 minutes is going to be 1 degree and 5 minutes. Am I correct? So what's it going to be? 19 degrees, 5 minutes west. Okay, that's it. That's it. Guys, good luck. Yes, we've done it. Every single thing that we've done, I can guarantee you it's going to be in the question paper. Take your time. Use a 10-minute reading time. Please use it. Yes, go through the questions. Choose your questions wisely. Okay, and don't forget your protractor to calculate your bearing. Determine your bearing. Magnetic bearing. Okay, gradient. Go over these facts. Once again, good luck. Yes, just good luck. Thank you. It's been awesome the last 6 months. And all the best. Cheers, guys.